Hello. 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 Good afternoon. Okay. Good afternoon, Jamalet. Good afternoon, David. Good afternoon, Olsmile. Good afternoon, Chloe. Good afternoon, Amy. Good afternoon, Diana. Good afternoon, Stephen. Good afternoon, Brooke. Good afternoon, Ashley. Good afternoon, Gianna. Good afternoon, Jaylyn. Good afternoon, Samuel. Hi, Jada. Okay, we're going to just get going here. It is still the case. Increasing numbers of you have gotten your, and good afternoon, Jasmine. I'm sorry. Good afternoon. Increasing numbers of you have gotten your exams back. Many of you still have not. The order has nothing to do with anything. And I continue to apologize. They're just coming back. When they're coming back, there's not much more I can say about it right now at this moment, but I feel your pain. I feel your pain. But they are coming, they're just slowly coming back to all the classes, one at a time. Okay, but let's get, and I know the semester is drawing to a close soon, for good or for bad. So let's get back to physics here. Obviously, any questions or concerns you could put in the chat. Including why does your board never work? Okay, what I want to get to, in fact, and actually, I'm going to drop the board in a second anyway. I want to get, okay. Okay, we're talking about electrostatic fields here. That is the topic. Last time you did we went over this computationally heavy problem to solve for the good afternoon, Nicholas. Good afternoon. To solve for the electrostatic field at a given point in space due to 2-point sources that were at nearby other locations of space. Like we did a lot of vector addition in all of this to compute the magnitude and the direction of the electrostatic field at a point. I'm going to remind you, I'm going to remind you that the equation that we used to compute that field is this top equation up here. Electrostatic field equals a constant times the magnitude of charge at a location in space divided by the square of the distance from that point in space to a separate location in space at which we are focusing our attention and at which we are studying the field. That's what the top equation says. I'm going to remind you one more time what it means. In other words, this is what it means. When we say this, right? Just to remind you or put in perspective, we did all this mathematical computation last time, but what was the concept we were saying? Was it that we were ultimately saying this? We were saying Okay, this is a summary of the concept we were using last time. Hold on, something in the chat. Just make sure. Oh, I got that. Okay. Charges cause field. When we're looking at the field due to a point charge, the limiting case, the extreme version, the elemental case of that which causes electrostatic field, if we picture a point source Q, right, capital Q, otherwise known as capital Q sub 1, right, the charge that's causing field is some point somewhere in space, right, labeled with this blue dot and this blue letter Q. The whole idea behind the field is that the field is the force waiting to happen at any and every point in space, everywhere in the universe, due to that point source Q, right? The whole idea is that Q deposits, if you like, a vector at every single point in space. And the vector that deposits everywhere in space is just a little vector that has, of course, magnitude and direction. The magnitude of the vector anywhere in space represents the strength of the force that would be exerted on some hypothetical, picturable, imaginable test charge, otherwise known as lowercase q, or otherwise known as lowercase q sub 2, right? Some hypothetical charge of positive 1 coulombs of charge. If you imagine a positive 1 coulomb of test charge located at any given point in space that you're imagining, then that 1 positive coulomb of charge would be forced with a certain number of newtons and in a certain direction by the original source charge Q. Right? So at any point in space, we believe there's this field, this number of newtons per each hypothetical coulomb of charge that could be found at that point in space, right? So we imagine a vector, or we model, we hypothesize, we imagine a vector at every point in space. The magnitude of the vector at every point in space represents the number of newtons per each coulomb of charge, positive charge, that could be located at that place in space. The number of newtons that each coulomb of charge would be pushed or pulled by the original Q, and the orientation of the vector sitting there at that location of space indicates the direction in which each imagined test charge of positive 1 coulomb would be pushed or pulled at that location in space, right? And I'm going to draw that in a different way in a moment. But again, what I'm just trying to reinforce here, that field, that field by definition is net electrostatic force per charge, right? I think something, I see something interesting in the direct chat. I'm going to address that in one moment. It sounds interesting. Hang on one second. So field is force per charge. If force is what a capital Q1 would do to a lowercase q2, if a force is an interaction between 2 points of Q, right, and it's measured in newtons, then a field is not measured in newtons, it's measured in newtons per coulomb. It's not an interaction between 2 actual objects, it's the interaction produced by one object waiting for the second object to come along, right? It's the interaction before it becomes if you know what I'm saying. It's the action created by a subject before or independent of whether there's an object actually there to receive this interaction. So one more time, I'm going to say force is
interaction between Q1 and Q2. Force is interaction between 2 point charges. Force is what 1 point charge does to the other point charge. But field is what 1 point charge does to any and every point in space, right? So, and I'm going to get this, I'm totally psyched for this thing that's in the direct chat. I won't forget it. Actually, I won't forget it because I'll go to it right now. But then I want to explain what everything I'm saying has to do with this like vector this little vector thing that I just drew there. Hold on, the thing in the chat. I mean, I think I know what it says. Okay, yeah, this is a very good question, chat. This is it's a very good question that's in chat. I will try not to go down a huge rabbit hole here. It's a very fair question. All right, so the question in direct chat is, Professor, is this like probability? The person's asking. Excuse me, sorry, I'm getting myself excited. I do get very excited when I talk about field. Okay, so the question in direct. Oh, okay, wait. So now there's a number of questions in direct chat. We're all good. So, all right, I'm going to go out of order for a second because the second question in direct chat, bear with me, says, I'm sorry, can you repeat what field is one more time, please? Okay, so that's totally fair. Let me, and I'm going to repeat it a lot. And there's different ways to say it. The main thing I'm saying right now, and then I'll go back to this probability question. The main thing I'm saying right now is field is force per charge. Honestly, that's the most straightforward way I can put it. Field is defined to be net electrostatic force per charge. I'll say it one more time. Like field, strictly speaking, is net electrostatic force per charge. If I'm talking about electrostatic field is net electrostatic force per charge. The bottom line is field is force per charge. The other thing I was saying about that, and I'm going to say it again, because, okay, again, this is like so many things in physics. This is super important, and it's a super big takeaway of this class. It's super simple once you get it, but it is not super easy. In fact, it's really not easy because it's so simple. So everybody who's like, feels like they're hearing me say something over and over again, please bear with me. It's simple in the sense that there's not many details to this, but because there aren't many details to unpack, I mean, there aren't many details to this definition. Because there aren't many details to unpack in the definition, it's hard to know what actually we're looking at. We're looking at something very fundamental here. So I have to say it many, many different ways and get you used to it. It's a simple idea, but the more you think, but it's a very abstract idea. It's very hard at first to like picture in a concrete or palpable, tangible way. It's very hard to see or touch or feel or imagine yourself seeing or touching or feeling this. So first of all, what I'm saying is field is force per charge. Okay, direct chat person who asked me to repeat that, and I'm glad you did. But another thing that I keep saying to expand that a little bit is I'm saying that field is force acting on space rather than acting on a second object. A traditional, regular, proper, everyday force that's measured in newtons is an interaction between one object and another object. That's what force always is, an interaction between one object and another object, between one thingy thing and another thingy thing. Field is one object interacting with space before the second object comes along to experience the interaction. So another way to put it in informal English is a field is a force waiting to happen, waiting to happen. I'm going to put it one last final way for the moment. Yeah, and please do keep these questions coming. Like really, honestly, even if we don't get to a million math, I want you to leave this course having some grasp of what field is, because it's so huge in the rest of your science life. People talk about fields all the time, and they're so real, they're so fundamental, but they're so hard to get your mind around, until you do. Okay, and believe me, and I feel like my mind is I love fields now, but it took me a while. I had to get used to them, and there's different ways to get used to them. But anyway, so I'm going to say one more thing, and then I'm going to get back to this probability question because it's a great one. One more way for me to say field is a vector valued function. A field is a vector valued function. What I mean by that is it's a function, right? It has input and output. It's a mapping between an input and an output. The input to field is location in space, or more specifically than displacement in space from some chosen origin or some chosen reference point, such as 0, 0 in a Cartesian plane, or such as some charge that we're looking at or something. So the input is a location in space, which could be best viewed as a displacement vector from some reference to wherever you're looking at. The input is a place that you're looking at, what I will generally call a location of interest, or what a location of interest, the location that you're interested in, or what textbooks and websites and stuff will often call the field point, meaning a point that you're looking at, a point in space that you're looking at to compute or investigate or measure the field. Okay, so the input is displacement. The output is a vector, a force per charge vector, a newtons per coulomb vector, a vector whose magnitude is newtons per coulomb and whose direction, whose orientation is the direction in which some 1 positive coulomb of hypothetical test charge would be pushed or pulled due to the original charge that's sitting there in space causing this field. The original charge that causes the field we call a source charge, and the charge that we're imagining or hypothesizing to experience the field is called the test charge. Now, I want to get to this probability question. I didn't even read it fully. I'm sorry. Here's the probability question in the chat. It's a really great question, and I'm not saying because I mean, the answer to it is not actually yes, but it's still a great question. The question is, Professor, is this like probability? Are we calculating the possible charge, but not necessarily the amount that would be observed? Okay, here's why this is really a great question. I'm going to dwell on it for like a moment or two, which means like an hour. No, I'm going to dwell on it for a second. First of all, it's a great question because the deeper you go in all of you, the farther you go in science, the deeper you go in science, and particularly the deeper you go in physics or say PChem, which hopefully most of you will take after this course, you start finding that really the kind of claims that we make about the physical world are increasingly probabilistic claims. And also, if you take statistics and stuff like that, it's very good to have it in your consciousness that a lot of times what scientists are actually talking about at the end of the day is probabilities, not definites. That's very good to have that in your mind. But to be honest, but to be clear, actually, that's not what I'm saying here. And I'm saying this again with total compliment to the person who asked it, but I want that person and everybody to pay close attention to me. Like, it's a good question, actually, because the answer is no, not because the answer is yes. Here's the deal. I'm not actually, I know the confusing thing that I keep bringing up is this test charge, this second charge, the per charge, the Q2 that got divided out of our original equation. Please remember, our original equation for force was like constant times Q1 times Q2 over R squared times these vector symbols. And again, by the way, for the moment right now, if you're trying to listen to me and get your mind around field, for the moment, don't even stress about the vector symbols and all that. That's is an issue, but it's not part of the thing I'm addressing right at this moment. What you want to have in your mind is that force, electrostatic force, is charge times charge divided by square of distance between them. Just like the gravitational force is mass times mass divided by the square of the distance between them. Okay, it's like that's like the point about magnitudes. Now, that's force interaction between two objects. What I'm saying is the field is the force before it even happens as a force. It's what force is waiting to happen due to one of the two objects, the one that we will call the source. Now, the field is there even before the second object comes along to experience it. The idea is the field is the amount of information, is the package of information sitting at every point in space, waiting for an object to come along and sort of read that information or access that information or incorporate that information and thereby experience a force. It's not a probability thing. You could say it's a prediction or a hypothesis if you want, or something, but it's not a probability thing because we're not calculating a number between 0 and 100%, or we're not calculating a fraction. It's not like PChem or quantum physics or anything like that, where we're saying we think the probability that there will be a force is like 3 out of 4 or something. And again, I'm not arguing, like I'm not dismissing this question. I hope it's a great question, but I can use it to make a distinction. We're not talking about probability here in the sense that we're not calculating a chance. We're not calculating a chance. What we're saying is, we're saying a very definite, specific thing, which is that for each and every 1 coulomb of charge that could come along to a given location in space, we know the exact force that each 1 coulomb will experience. If I say that the field at a point in space, is 30 newtons per coulomb in a northeast direction, what that means is that I'm saying definitively that right now there might be no coulombs there at all. That's fine. I don't care if there's no coulombs there at all. There's 30 newtons per coulomb. There's a vector with magnitude 30 newtons per coulomb pointing in the northeast. And what does that vector indicate? It indicates there may be nothing there right now, or there may be something. We don't care. We're not predicting the chance of there's something being there. What we're saying is, for every single 1 coulomb that could ever or might right now be there, for every 1 coulomb of charge that's there, it will experience the 30 Newton force in the northeast direction. It'll be pushed or pulled to the northeast with an amount of 30 newtons. In other words, if there's 2 coulombs of charge there, then the force that if there's a point charge of 2 coulombs, then that point charge will experience 60 newtons to the northeast. If it's 3 coulombs, it'll experience 90 newtons to the northeast. In other words, if I say that field is force per charge, I'm the corollary of that, I'm correlatively saying that force is charge per field. And what is that? So the field is all the information that we need to know what will determine this force. It's all the information due to the source and due to how far away the source is. It's all that information in a bundle ready to be multiplied by whatever amount of test charge sits at that location. We're calling it a test, not because we're predicting like what's the chance that there will be a test there. We're calling it a test charge rather than just calling it the receiver charge or something. We're calling it a test because what we're talking about, we're saying we know in advance all the information that will be applied to the test. And we have a simple formula. We're saying if your test is 1 coulomb and your field is 30, then your force is 30. If your test is 2 coulombs and your field is 30, then your force is 60. The field is the bundle of information that will be applied to each 1 unit of whatever receiver is there to receive. And what we're saying is this bundle of information is there even if there's nothing there to receive it. Let me see. Oh, wow. Okay. I was just going to ask if I could get follow-up from the person who asked this probability thing, and that person did follow up. And he or she is saying, oh, so it's more like potential. He or she is saying, oh, so it's more like potential. And yes, if I had to make an analogy here, everything I'm saying is far more like potential than it is like probability. It's an analogy. Of course, this is not exactly potential. The units are different. The exact math is different. It's not exact, but yes, conceptually, qualitatively, this is a potential in exactly that way that the person's saying, in that it's true, ready to be actualized, whether or not it gets actualized. Yes. And it is a definitive number. Yes. This is good. These are good questions. And hopefully that this is helping. And I'm going to say one more thing. And today, and by the way, it's a little bit hard to picture. So the main thrust of today, yesterday, last Wednesday, you all followed me in doing a fairly thick computation just to calculate the field at a point due to 2 points of charge. Today we're going in the other direction. Today I want to try to help everybody picture this situation much more. Like it's not going to be computation heavy today. It's going to be picture heavy today because they really want you to get your minds around this idea. So these questions are great. And if you're trying to be conceptual today, and for some of you, that is, of course, more relaxing or more enjoyable. And for some of you, today is the day to literally ask these questions and be like, wait, but is the field blah or is the field blah? Like I'm going to show you a bunch of pictures and really try to help with that. But the math is like everything in physics. I hope you're used to at this point. The math, we all think the math is the problem, but I think we all secretly know at this point, the math is not the problem. The computations are not, you all know how to do computations. It's setting up the computations. That's the problem in physics. And that's because we have to know what to picture in order to set up the computations. So that's what today is for. So I'm going to say one more thing, and then I want to really ask the two people that have been in direct chat so far. I mean, they know who they are. You know who you are. If in a minute or two, if you could follow up and just let me know if it's getting, it can't be 100% clear today, but if it's getting more clear to you two people in the direct chat than it was 5 minutes ago, that would be really helpful for me to know. I want to remind you all that so field literally is the information at each point in space of the force that will or would occur at that point in space if a second object would be at that point in space to experience the force. And where does the force come from? A first object. Whenever we talk about field, we talk about field due to a source. Source is the first object that creates the field, and the field is the information everywhere ready, like as a package that looks like a vector in our minds, ready to push or pull any second object that could come along to those points in space. Every time I say that, of course, it sounds a little abstract. This is a new idea. This is a weird idea. I'm talking about information sitting anywhere and everywhere in space in the form of little vectors. Now, again, let me remind you two things. One, I'm not literally saying that there's literally like styrofoam arrows everywhere in space. Arrows are just the way our minds most simply and productively can picture this information. I don't know how the information's actually there, but since the information is dictating a force with magnitude and direction, it's easiest for us to picture all the information as little arrows. So that's number one. But number two, if you say, why do we have to picture information in space now? Like, what is this? Like, remember, that's the point of this course. The point of this course is to get our minds around things that matter that aren't matter. This course is about unthingy motions through time and space. And what I'm talking about right now is no longer masses sitting in space. I'm talking about information sitting in space. But where did I come up with this? Why? Like, why do we even believe in it? Why do we need to believe in it? How is this part of science? Remember, it's coming up. Fields are coming up because we have at least two forces that we've stumbled on that seem to indicate that objects in the universe pull and push other objects in the universe without touching them. Objects seem to interact, masses and charges seem to push and pull other masses and charges, A, through empty space, at a distance, without touching them, and B, they seem to pull and push through empty space without touching in a manner that is precisely quantitatively determined by properties of these two objects that are not touching, i.e. a proton pulls another electron within a number of newtons that is precisely determined by how much charge the proton has, how much charge the electron has, and how far away apart the two of them are. And when the electron moves, the proton finds out that the electron moves and gets a new R to put in its denominator and thereby calculate a new F to exert on the newly located electron, right? What seems to be true is that objects in space know how far apart other objects are in space from them and know how big they are. So we don't really know how this works. Nobody really knows how the universe does this. But as far as making predictions about it and organizing it in our minds, we say, okay, if the information of charge 1 over here is somehow accessible to charge 2 over there, the information must be somehow in space. And we call that supply of information, or that medium of information that's everywhere in space, we call a field. Okay, we don't really know what's going on, but the field model or the field concept is the one that seems so far to be fitting in our minds most coherently and harmoniously, and the one that seems to make the most accurate predictions. So that's what the field is now. Okay, cool. I'm seeing things in the chat. I totally appreciate the honesty in the chat, and people are admitting in the chat they still don't maybe fully get it. I mean, they're saying, one person in the chat is saying, like, I kind of see now. I appreciate the honesty. Really, honestly, if anybody said they fully get this right now, I mean, I would be a little suspicious of that. But if you're just getting it more and more, that's the idea. So I'm going to move on, but keep this coming, all of you. I'm going to move on. I'm going to say one thing. We're going to talk a lot about vectors today, but in a conceptual way. I also want to change, but please do keep these. I to this day, is this worth saying? I will just say, to this day, when I first became a physics major, undergrad, so that's like 33 years ago. Is that right? How could that be? Well, something like that, whatever, like 35 years ago, when I first was becoming a physics major and thought I was interested in these ideas and and I was just starting to get it, and I thought I liked it, and I was signing up for it. I was on a chairlift with a guy. I'll just never forget this. I mean, I was skiing. I was on a chairlift with a guy who was a physics major and was ahead of me at a different school, whatever. And we were talking about something, and then he started talking about, we were just yammering on this chairlift, but he started saying something about, oh, well, then, but then the gravitational field would blah, 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 blah. And I remember my heart sinking. I was just starting to get physics and just starting to think that I liked it. And I just committed to this physics major. And then this guy who I liked, and who was a nice guy, and whatever, he started talking about field on the chairlift. And my heart sank. I was like, oh, field, right. Physics has something to do with fields. I was like, I thought two things in that moment. One, I do not know what a field is. I do not get this idea of a field at all. And two, I thought, and this guy's talking about it like it's like a comfortable idea, like he's like cool with it, and it's just like part of his vocabulary. And it was so intimidating to me and so distressing. I was like, maybe I'm not cut out for this. I mean, this is 33 years ago, and I remember thinking, maybe I'm not cut out for this, because I guess fields are like a big deal in physics, and this guy's talking about him like he's not freaked out by them. And I can't imagine the day that I'm not freaked out or confused by the notion of a field. Well, I will say this to all of you. I still remember that to this day, thinking I'm not cut out for this because of fields. I'm glad I had that moment, because at least in that moment, I was recognizing that there was something to fields that were a little bit like that felt over my head. And I didn't get them right away just because of that conversation. I didn't. It took me a while. But I do get them now, I think, as much as I get anything. Like I think I'm comfortable with fields now, but it's partly because I recognize that they are there, that there's something going on that's not like my obvious normal way of thinking or old way of thinking, and it requires like a new way of thinking. And I eventually got there, but you don't get there if you just are like, yeah, do the math, and okay, yeah, like I'm sure it's like whatever. Like, anyway, you get my So bear with me. If you don't fully get fields yet, but you're feeling like you're getting maybe a little bit more, then you're doing the right thing. And you're on the right track. And we're going to do more of it today. I'm going to shut up, but I'm not going to shut up, but I'll shut up about this. One thing this diagram is trying to say, you'll notice that in every equation that I write about fields, there's like this R hat and all this R going on. Remember, I want you to know R vector, R with an arrow over it, is a displacement vector. vectors that we first learned in 203. It's just a distance and a direction from one location to another. In particular, with fields, our vector is the vector of displacement that by definition always points from the charge that's causing the field to the location of interest, the point P, the field point, the place we're looking. The whole idea, and we're going to see in a moment, the whole idea is that Q, if Q is a charge in the universe, it's putting vectors everywhere. It's creating fields everywhere. It's creating a field everywhere. But at every location you look, there is a vector there that is determined okay. At every point you look, there is a field vector there whose magnitude and direction is determined by the vital stats, the magnitude and position of the original source charge Q. Now, so what I'm saying is R, by definition, always points from Q, from the source charge, to the location that we're looking at. So R is not the field vector. R is not the field. R is the displacement from the charge to the location we're looking at. Any vector from here on in can be viewed at, well, from always, can be viewed as a magnitude, a pure magnitude times a pure direction. The pure direction is known as R hat, the unit vector R, that R with the caret over it. The unit vector R is defined to be the vector, the entire vector R divided by its own magnitude. So like, R with a caret over it, R hat, is a vector that by definition points in the direction of the original R, but only has a magnitude of one unit. It's a unit vector. It's just there to show direction, to indicate direction, and to not have any particular size. The whole point of it is to allow us to break up our vector itself into its constituent parts, its pure magnitude and its pure direction. So the idea is that the electrostatic field vector that's literally sitting there at P, that's telling us how strong something would be pushed and in what direction, E is a vector that has magnitude and direction. Its magnitude is constant times Q over R squared. So its magnitude is determined by the original magnitude of charge times a constant times the square of the distance between Q and point P. Like, notice in the equation up here, the equation that I'm talking about, the equation that gives us field from a point charge. Notice what's in the denominator is just the letter R squared. The letter R without any symbols over it means the distance R, the magnitude of the displacement vector. You take that distance, square it, and put it underneath the charge magnitude and multiply it all by this crazy constant. And then the whole thing gives you the magnitude of the vector that we're computing, the field vector. That's the magnitude. Like, this whole thing is the magnitude of the field vector. What's the direction of the field vector? The direction of the field vector points along R hat. The direction points in the same direction as a line that you could imagine in your mind from the original Q to the final P. So that R hat, so all of those numbers together give you magnitude, and then the R hat gives you direction. So in the end of the day, you have this field vector. The E field vector is a vector constructed from the direction of the original R vector and constructed from the magnitude of the original R vector along with the magnitude of the original charge. Bottom line, what I'm trying to say, and I will move on, I promise, sort of. What I'm trying to say is this E arrow that's sitting there at point B is a bundle of information. It's all of the information of the original charge magnitude and how far away and in what direction the original charge magnitude. It's saying so it's saying this is what's going to push or pull each and every one positive coulomb of charge that could be located at P. Okay, I don't know if that helped at all, but so that's how one source charge creates a field vector at a location. Okay, so here's now I want to shift my attention. Now, hopefully you can follow this abstraction. What I just showed you there was how like a point over here creates a field vector over there. Over there is just one place that we were looking at. But that's just one place we chose to look at. What in general is a point source doing? If we have a positive point source plus Q, in general, what you can imagine is that so this is a vector field diagram of what's happening in general in space due to one point source, one positive point source. What we're saying, now this is a representation. I've picked just enough I've drawn just enough vectors to indicate the pattern of what's happening in space in general. The idea is that for any, remember, a field is a vector valued function. So the idea is that any point in space you imagine, any point in space you're interested in, there's some vector sitting there with a certain length and a certain direction. Here's the pattern of what they look like. Notice that if the source is positive, anywhere you go in space, you would be pushed out away from that source along the line connecting the source to you. Like wherever you are, there's a vector that's pointing along a radial line and pointing out along a radial line, right? Because the idea is because the field is how much force and in what direction would be exerted on any and every one positive coulomb of hypothetical test charge. This is a picture of what would happen to each coulomb of positive test charges. Well, positives get pushed by other positives. Positives repel other positives, right? So if fields can be caused by anything. Fields can be caused by positive or negative, but the field is always our hypothesis, our prediction, our potential, so to speak, of what would happen to a receiver who was positive in charge. So any receiver would be pushed by this positive source, and it'd be pushed along a line connecting the two. But the farther away it would be, the less it would be pushed, right? So you have these radial vectors of decreasing size spreading out from the source charge. This represents, and this goes on forever. The idea is that no matter where you are in space, there's some little arrow pointing away from the source, and the farther away you are, the smaller the arrow is, right? And if we drew this all to scale, each arrow represents the number of newtons that each coulomb of test charge would experience at any various point in space. Okay, so that would be the vector field diagram for all of space due to a positive point source. If you're following what I'm saying, then I think you might follow also. Then if Well, I don't have to keep writing this. So if we have a negative point source, which is possible, like we have an electron or a bunch of electrons jammed together in a tiny space, producing field, totally conceivable, then this picture would look very similar, except for one correction. It would look like this. Again, arrows getting smaller and smaller and smaller as an inverse r squared function of distance. But these arrows, and of course, I'm not, in principle, this would be drawn to scale, and I'm just drawing enough to show you the pattern, but these arrows all point in because, again, the field is a representation of what would, in other words, the test, and I didn't get this for years, for semesters, I didn't, the test charge that we're picturing in our mind for a field is always positive 1 coulomb of charge. This whole thing is about what would happen to each and every 1 coulomb of positive test charge. The source could be either one, but the test is always positive. So if the source were negative, the idea is that negatives pull in, because any positive that would be out in space would be attracted to the negative, right? So it looks the same as the other picture, but the arrows are attractive. They're pulls rather than pushes, okay? And I might add, too, how this works with negatives and positive signs. If you go back to the original equation, strictly speaking, oh, here goes the board, of course. If you go back to the original equation, board might disappear in a second for a small change in pace. We'll see. Okay. There's really a plus. Oh, what? Yeah, the board. Oh, the board's frozen. All right. You're going to lose the board in a second. I'll just talk for a second while the board catches up with me, so to speak. Remember, the direction of the field points along R. Like E is a vector, R is a vector. They're not the same vector, but they absolutely point along the same line. They have the same direction. Okay. They have the same direction because the E vector is equal to a bunch of numbers times R hat, right? That means E and R point along the same direction. Now, they're not the same size, but they're along the same direction. However, the E, now putting the board back, you picture the R vector first. R points from the source to the test, or from the source to the field point, the location of interest in space, right? But then you plug in the charge magnitude, the charge of the source. The charge magnitude is either positive or negative. Hold on, I'm doing two things at once. If the charge magnitude is positive, then your whole answer is a positive number. And that means that your whole answer points positively along the direction of R. So your whole answer, the field pushes out along R. If the charge magnitude, the original point source that made the field, if it was negative, then you plug in negative blah blah for Q, right? And you'd have a negative sign in your answer. So, and when I say your answer, I mean, here it comes. I mean, you'd have a negative sign in your answer from this top equation at the top, that, after you plug in the constant and you plug in a negative number for Q and you divide by R squared, of course, R squared will necessarily be positive. Your whole thing will be negative. So what does that mean? It means the direction will be negative times R hat. It means the whole thing will point along the negative, the opposite of R hat. That means if your original source is negative, the whole thing points against R. It points in from the field point to the original source. So it's a pull. It's attraction rather than repulsion. What I'm trying to say, if you want to write something down, I'm saying in these kind of fields and and action at a distant forces and stuff, whenever we get a negative sign, that means attraction or pull. And it works with the vectors when you think about it that way. When we get a positive sign, we get a push. Okay, anyway, so this is the field line, this is the vector field diagram from a positive point source. This is the vector field diagram from the negative source. Now we're going to go one step further. We have 24 minutes. Okay. Should I add? Okay. But this is a lot to draw. And notice everything I've been saying so far today and last week was all about the field that would be caused by any and every one dot of charge. In reality, we have lots and lots of dots of charge. We have lots of points, which together make up big continuous shapes of charge in the world. And ultimately, what we're really interested in is the fields caused by actual real objects, real shapes, real, say, atoms and molecules with lots and lots of protons and electrons distributed in all kinds of arrangements. So we ultimately, if the diagram that we would have to draw or picture in our mind just from one dot is this elaborate, we're going to get into real trouble once things get any more realistic. So we develop a new technique. We build a new technique for picturing and computing and predicting fields. We build a new technique from this vector technique. Okay, so I'm going to show you so vector field is the first way to picture fields. To picture a field due to a source charge, you picture a whole bunch of arrows everywhere in space. And that's not wrong. And you can hold that in your mind for the rest of your life. It helps, but it starts getting like to be a lot of information to hold in your mind the more and more elaborate these situations get. So we have another kind of model or picture for representing and mapping fields, and this is called the field line diagram. Instead of vector field diagrams, we do this thing called field line diagrams. And instead of picturing vectors, when we're picturing fields, we start picturing things called field lines. You may have heard of them in other classes or on the web or something. Field lines are field lines are to fields as vectors are to velocity, acceleration, force, and everything. Field lines are absolutely our tool for discussing and analyzing fields. So here's how they work. So the idea behind field line picture is we take all the vectors that were in a vector picture and we connect them all up. So we have a lot fewer lines to deal with. In fact, let me just cut straight to the chase. I'm going to switch. Well, no, okay. I will cut. Okay, looks very similar, right? So what I'm saying is the field line diagram, we connect up all those arrows. Instead of arrows that are getting smaller and smaller, they're just all strung together into one big arrow. And instead of a pattern of arrows getting smaller and smaller forever and ever, we just have a arrow that goes on forever. Doesn't look like a big change necessarily, but it is. Okay, and similarly, I'm going to go similar. So these lines, they radiate, they go on forever, and just cut to the chase. If I do the field line diagram from a negative, so these go on forever as well. But they go in because it's negative. Okay, so it doesn't seem like a big thing, but I'm gonna because I think you can do that fast. I'm gonna turn the page when I know we have 17 minutes. I'm gonna turn the page. Okay, this is very important. We've got 15 minutes. Okay. So all we did was connect up all these arrows. Doesn't seem like a big deal. Right now, for the moment, we're doing that so we can save ourselves having to draw as many arrows. But we still have arrows, we just have fewer of them. So the direction of the arrows, I mean, so the arrows are still being used to represent a quantity with magnitude and direction, a force waiting to happen. The direction of the force per charge, the force waiting to happen, the direction is still going to be indicated by the orientation of those arrows. Like where a tip is pointing, that's the direction in which the force is acting. But magnitude now is a different issue. Like the question here is, how do we represent magnitude now? See, in the vector diagrams, magnitude of force is represented by length of arrow. But now length of arrow is no longer part of the picture. All the arrows are connected up. There aren't any more arrows of shorter or longer length. All the arrows are just one big arrow that's going on forever. All the arrows, in effect, have either an infinite length or a length. The arrows don't have a length anymore that means anything about magnitude. So how is magnitude represented now? The answer is this. The answer is that the closer the arrows are now, the closer that the lines are now, the stronger the field is in a particular region of space. So the answer is density. Now, like if you look back at this picture, either of these pictures, you notice that close to the charge, we don't have longer arrows anymore, but we do have arrows that are closer. We have lines that are closer. Close to the charge, the arrows are fairly dense. They're fairly crowded. There's a comparatively high number of lines per unit space, per unit area on the page that I drew this representation. And as you get farther and farther out, the arrows, the lines are spread out more. So the more spread out a bunch of arrows are in a region on the page, the weaker we understand the field to be in the region of space represented by that page. If I were drawing these to scale, I would literally have a scaling factor. If I were rendering these on a computer or something, I would have use a consistent scaling factor so that we could actually infer quantitative magnitude of something out here from how many lines there are in the area of the page out here, etc. So now in this new representation, density of lines indicates magnitude of field, or I should say density of lines per unit area on the page represents strength, magnitude of field in the region of space represented by that page. What I'm going to do now is we have 12 minutes. I'm going to switch screens and show you a bunch of different field line diagrams now from the web, just from Google Images, you could do the same thing. Just to give you a sense of what's going on here, of how these work and why. All right, so I'm going to switch, but definitely stop me. Oh, you're kidding. Okay, yeah. So here first, so this is just from Google Images. I mean, it's not, from LibreText, but if you just type EFieldLines or field line diagrams into Google Images, you'll get a million things, such as this. First, what's on the screen right now is not field lines yet. This just brings us back to what I was saying a couple minutes ago, just a nicer rendering. But I was saying, like, if you have a positive charge at a positive source, point source, at the origin of some three-dimensional coordinate system, then the whole idea is that everywhere in that coordinate system, there's a little arrow pointing out from the positive point source, and the arrows spread out, they radiate out from the point source, and they get smaller and smaller as you get farther and farther away. Those are vectors, right? But you can see that if you're trying to draw with any precision, or you're trying to account for three-dimensional space, it's a heck of a lot of vectors you have to draw just to talk about the field from one point. So instead, we connect up the vectors. Okay, and now look to the picture on the left for a moment. Yeah, I'm just looking. Okay, if you look at the picture on the left, that's what I just badly drew on my board. That's the field lines from a positive point source, right? So the arrows are now connected up, and they're denser, closer to the point source, and they're less dense, farther away, as we believe field to be. But now you see, with this field line picture, we enable ourselves to start accounting for more complicated situations, such as letter B on this picture. What's going on with letter B? Letter B, as it says, is the field line diagram due to two point sources, kind of like what you were mathematically, quantitatively trying to solve for last Wednesday. If you imagine, only these are equal, these are opposite charges, just like you were doing on Wednesday, but these happen to be equal in magnitude. The ones you did on Wednesday were unequal magnitude. We'll talk about that in a minute. So if you imagine that there's like a proton over here, where the blue is indicated, the dark blue is indicated, and you have an electron over here. What this picture now, and follow me this, especially if you've been, this is all very abstract, but please try to follow. I'm saying this picture, these field lines that you're looking at in portion B of the web share, these field lines are not a picture of what the positive is doing to the negative. That is not what this is. This is a picture of what the positive and negative together are doing to all of space. The positive and the negative here are both together as a pair, the source of field. In other words, we're taking a step now and looking at what if we have 2 point sources together creating field, much like we did on Wednesday. Now, Wednesday, remember, what we were doing was doing all the numerical calculations to figure out what would happen to us at one point in space, one of the points in space due to these 2 point sources. So it was the same kind of setup, but it was a different question. We were trying to calculate the length and the orientation of the one vector that would be pointing at any one given location in space due to this pair of sources. Now, what this picture is saying is, what if we just want to depict everywhere in space, like the pattern of pushes and pulls that's going on, ready to happen everywhere in space due to this dipole, this equal and opposite set of point charges. In other words, so for example, this is like a hydrogen atom, right? It's got a proton in the nucleus, and then over here it's got a electron in the cloud, right? And together they're affecting the world. We're not talking about how they're affecting each other. We're talking about together how they're affecting the world. And so what this picture is right here, I'm looking at the time, we have 7 minutes. What this picture is right here is, if you drew a vector everywhere in the world, that was the vector sum. If you drew a little arrow everywhere in the world, that itself was the vector sum of the vector coming from the positive plus the vector going toward the negative. In other words, if you drew a vector everywhere, that was like the result of the calculation we did on Wednesday. And then you sewed up all those vectors and connected them so you didn't have to draw a bajillion of them. The picture would look like this. Now, note, this is a very different type of picture now. It shows you in a very important pattern. With this picture, if you pick any point in space that's captured in this picture, any point in space, any point in space that you pick, the orientation of the line nearest to you shows you what direction you would be pushed or pulled due to this dipole, right? So for example, if you pick the point directly equidistant between the, can I do this on the, I can't, yeah, can you see yeah, you can, okay. I put my cursor like right in between the two. I could probably even type something. There's an arrow pointing from the positive to the negative. Now, again, let me say again, that arrow pointing from the positive to the negative does not mean that the positive is moving towards the negative or something like that. It means if you imagined a positive 1 coulomb of test charge sitting there at that location, equidistant between the two, the 1 coulomb of positive test charge would be pushed by the other positive, and it would be pulled by the negative, right? So it'd be pushed away from the positive, it'd be pulled toward the negative. It would instantaneously be pulled or pushed to the right, or however you see it on your screen, right? It would, if nothing else were going on, it would instantaneously, a test charge would accelerate from the proton to the electron. And if you look at the lines that are there, right in between the two, there's a bunch of lines, they're all crowded together, meaning the field would be pretty strong there. It would be pushed pretty darn hard. Why? Because the push from the positive is reinforcing, is all like the positive is pushing you that way and the negative is pulling you that way. All the vectors are totally lined up. They're totally in agreement with each other. So it would be like vector plus vector. What do you get? Big vector. So the lines are crowded there. The lines are dense because the magnitude of the force that would be experienced at that point is comparatively high. It's very strong. If you go way up here, if you can see the cursor arrow, if you go like way up here, okay, to this arrow way at the top, well, and this is the last example we'll do for today, but that arrow again is indicating a force pointing from left to right. Okay, why? Because really what's happening there is the positive is pushing up and to the right. Remember, positives push and negatives pull. So the positive right at that location is depositing a little vector that's pointing up and to the right along the radial line connecting location P to point source Q. So there'd be a little arrow there pointing up and to the right due to the plus. Then there would also be an arrow. Now follow this, and we're almost done, but please bear with me here. There would also be an arrow at that location, at this location that I'm hovering. There would also be an arrow pointing down and to the right due to the negative point source, right? The electron in light blue. There'd be two vectors there, one from each source. We would add those two vectors together like we did last Wednesday, but one vector is pointing up and to the right, the other is pulling down and to the right. Why down? Because negatives attract, they pull, right? And the other's up because positives push. So you'd have an up to the right arrow, and you'd have a down to the right arrow. The ups and downs would cancel out. All you'd be left with is the component to the right. So you'd still be pushed to the right if you were up here at the top, right? But the magnet, so the vector sum would still be like a little arrow pointing to the right. But the magnitude of it would be a heck of a lot less, because if you plug in all the numbers like we did on Wednesday, you're way farther away from both of those charges. So the vertical components would cancel out. The horizontal component would be left. The horizontal component would be a lot smaller than in between the charges. So what we get up here is we get rightward pointing things, rightward pointing lines that are far less dense. The density of lines up here is less because the magnitude of force per charge is less. And the same type of argument goes anywhere you are in this whole thing. We have 1 minute. Notice field line diagrams, field lines, as opposed to vectors, follow a whole different set of rules. Field lines can be curved. They are curved. Field lines go on forever, or they land at a negative. I mean, I'll write all these rules down for you on our next class, but field lines are drawn differently from vectors. Field lines represent the sum of all of the vectors happening at any spot. And the bottom line is the tangent to the field line indicates the direction of force per charge, and the density of the lines in any region indicates the strength of charge, the magnitude. And so you can get all kinds of complicated pictures like this. We'll go over this on next class, but you can see that the more and more complicated your situation is, the more and more complicated the line pattern gets. But it's always a pattern. It's always a pattern. And the pattern represents the pattern of the things causing it. Okay, that's enough for that. It's 1:30. I'll hang out for a second if there's any questions. Thank you for being with me with all of the stuff I owe you, and we'll just keep going. You don't owe me anymore unless you do. I will see you Wednesday, and I'll be in campus tomorrow, in my office tomorrow, if anybody wants or needs anything. Oh, yeah, I'm sorry, but you guys. Oh, sorry. Okay, Sam. Yeah.
Hello, Professor.
Oh, hi. Wait. Oh, let me. Yes. Let me. Can I close the screen share so I can see?
Yeah.
Okay. All right. But I'm listening. I'm also, for what it's worth, I'm going to stop the recording just so you can ask whatever you want. And people, hold on.